Okay, good afternoon, everybody. Welcome to Wednesday. All right. I know I had one quick update. I'm trying to remember what it was. Midterm 1, midterm 2 dates. So I've heard from lots of you. I understand, yes, there's an amazing conflict where bio is on the same day. Part of my brain is like, haha, that's what's called growing up is this sucks. I'm not going to do that. The biggest problem is why this is slow. There are so many exams being mapped over this time. It's taking me time to find an alternative day and alternative time. As soon as I know where those blocks are, my intent right now is yes, I will move them so they're not on top of the same day as bio. I don't remember the number of it is. 234. I don't understand why I'm always the one that has to move. This really sucks. You know, they should be half the ones that moves. We're cooler than them. But it's taking me some time. My goal, though, is just to put everybody's fear to rest. I do want to move it probably 1 day or 2 days. The question I want to ask the class, though, that same week, same points, does that create a new conflict somewhere else? If that bumps over to Wednesday, what happens? So does anybody, again, fill me in. What is on the evening of the Wednesday of that week? What other class has a midterm there? 10th or the 11th of February? The 11th? Oh, God. Sorry, yes?
Like Wednesday, Thursday.
Yeah.
And then this was like their 8 a.m.
They're 8 a.m., but we're in the evening, so haha. Okay, like I said, at the moment, I have no confirmation because I have no room assignment on that point for those other days. I'm looking at what other options, and I'll put them up onto Piazza and that on Canvas to sort of try and do. Again, I'm doing my best to stay away from other conflicts as it is. This is the fun of like having multiple classes running at the same time. I will try my best, though. All right, where we left off last time was protecting groups. We talked about aldehydes, ketones, and the formation of these acetals from diols to give you these protecting group compounds. Remember, the protecting group temporarily hides the carbonyl functionality to allow you to do other chemistry. You're taking advantage of higher reactivity in order to sort of erase it. We also brought up the concept of imines. These are nitrogen equivalent of what we used to be doing with the acetals. Same mechanism. You're just using a nitrogen nucleophile in place of an oxygen nucleophile. The thing I really want you guys to focus on now as you're learning these mechanisms, look at what's similar for the imine mechanism versus the acetal or the ketal mechanism. One of the best ways to look at these two is step by step. There are some things that are almost identical. There are some steps which are slightly different. If you identify something of like, why is it this way with nitrogen and this way with oxygen, there's a reason of it that comes down to pKa, relative stability, something like that. But those flagging those differences, focusing on them and understanding them is a key for understanding all reaction mechanisms. So it's a really good way to go through. As we kick off, take a second. What are the products of the reaction I'm showing you here? Okay, time. Turn to the person next to you. Argue this out. What are the products? How many products? Why are those the products? Okay, time. So quick question. How many products are there in this reaction? 1, 2, or 3? There are how many products? Okay, so 2, I see 3. You're both kind of right. You're missing one piece of information that makes that sort of congruent. What's that? There are 2 equivalents of one molecule. There are 3 molecules I might draw. I agree. 2 different molecules. Well, that would be one to describe it, right? That's the real focus. So, when you're taking apart a reaction like this, first off, look at your starting material, look at your conditions, identify key function groups as part of what you're doing when you're studying, especially as we're giving you this content walking through. A key way is to use the question against itself. We're talking about acetals and ketals. Find the acetal or ketal. That's probably what we're focusing on for chemistry, right? That's the key piece here. So there's where the center of reactivity is. Reactions are going to happen focusing on that carbonyl, or that mass center, that mass center. That's where the business end of this molecule is. Okay, look at the conditions. You have, what is this, an acetal or a ketal? This is a ketal. It's part of a ketone, right? There's carbons on both sides of the center of identify. I'm using water and TFA. We mentioned that last time. TFA is what? That is trifluoroacetic acid. If anybody likes chips, fries, not British, fries, and you really like it with malt vinegar acetic acid, you're crazy. That's what my dad used to do. That's insane. Why would you do this? But trifluoroacetic acid would be even more sour. It would be the best additive for your fries ever. I'm trying to give you a visual to remember what this is. This is a powerful acid that will eat through lots of things. It's an acid. You've got an acid catalyst. You're in a THF solvent. You've got water as a reagent. We are doing hydrolysis. We are breaking down the acetal or the ketal. We've got them formed. We're actually doing a deprotection step. So what that means is I'm going to be cleaving these bonds. I've indicated these because the center of the acetal, the carbon of the acetal, that's the carbonyl piece. The 2 carbon-oxygen bonds, those were alcohols. That's where my carbon-oxygen sigma bonds were my alcohols, and I'm forming them as I go through this. Which means if I cut this apart, I'm going to have one molecule like that, and same thing on the other side. When I cleave this, I'm breaking down that carbon-oxygen bond by doing my protonation, my water addition. It's the reverse mechanism if you did for the formation. So I've got 2 of those. That's why we've got 2 equivalents, same molecule, right? Just left and right hand, same piece. The stuff in the middle, this part right here, again, stuff that isn't changing, still have a 6-membered ring. The 2 carbons I've indicated there and there are now carbonyls. You're regenerating the carbon-oxygen, and we've got 1 on either side. It's a diketone and 2 diols to make this diacetal we have through here. 2 different molecules, 3 molecules altogether. Good? Okay. All right, so for today, we're going to dive back into imines, talk about examples, talk briefly about the oximes and hydrazones, and start talking about enamines. Now, when you see that name, remember, imine, we talked about last time, is talking about a carbon double-bonded nitrogen is our imine structure. What we called oximes and hydrazones, that's talking about what's different out here, but it's still the same carbon double-bonded nitrogen. Enamine, what does that sound like? You may have heard stuff like this in 203. You've seen us name stuff like this. Enamine is made up of 2 functional groups you've heard of before. Yeah, ene is what? Yeah. Yeah, that's how you're making them. Yeah, again, this is why I just want to call attention to this, is it's made of 2 pieces you've seen. And ene is what? Carbon double bond carbon, right? That's an alkene. Amine is our nitrogen with stuff attached to it. So what you'll see is it's actually made up of these 2 functional groups in the same place at the same time. Has anybody heard of an enol before? This is something you probably touched on in 203. Same idea, right? Organic chemists are not that creative. So we have our imines. Again, primary imine is referring to this substitution. Secondary, substitution here. Tertiary, we have 2 groups on them because of the bonding order of nitrogen. When we go to this guy here, two R groups on nitrogen and the carbon-nitrogen double bond, it is always going to be positively charged. It is our iminium species. So you get this charge notation in the name. Oximes, different here. Hydrazones, nitrogen here. Enamines are made up of an alkene and an amine. You see the double bond is just not represented here. It's actually slid over where you have a double bonding relationship to the adjacent or alpha carbon. So they look like, and that's why we stack them up this way. These two are cousins of each other. They can be formed or interconvert, where the only thing that's different between my iminium structure is if I had a proton over here, losing this proton forms that guy. Now it's the general form is the iminium. The specific form, if there's an alpha proton I can lose, gives me my enamine. But that's where they're related to each other. And we'll talk about that in a little bit later at the end of class. So we mentioned last time, how we form them depends on which type of nitrogen we use. They all come from aldehydes or ketones as our carbonyl-containing unit, and then it's what type of nitrogen we add to the species, where if I need to make a hydrazone or an oxime, you got to bring those species to the party. They're coming in attached to the nitrogen, where the business end of the reaction really is about the NH2 structure. That's what's common for all the imines, oximes, and hydrazones. Okay, so we're going to go through this mechanism. Last time I gave you the general mechanism. I wrote it out longhand at the end and I recorded it out. You guys should go watch that one for an update. We're going to go do it again live here because this is a case where, like what we started to talk about before, you're doing this additions, following the sequence of reactions. I'm making it slightly more complicated because I'm coming in with a single chirality of my nitrogen nucleophile. And the reason we use this is one part, I'm trying to train you guys out about geometries of products that are possible. But on top of this, look at which centers are coming along for the ride, not part of the mechanism, not impacted, versus are being formed or geometry is changing as a part of the mechanism. This is something we teach you guys through with things like SN1, SN2. The center of reactivity is suspect. It may form enantiomers or stereoisomers, but we're doing a reaction at a specific atom. The center I've designated here, this S center, here and here, that's how I map this out. That center becomes this center. It's just coming along for the ride. It does not change as a course of this reaction, which means if I start with a single enantiomer of my primary amine, when I run this chemistry, that stereocenter is just being reflected or brought along to the product. Okay, there's still possibility of stereoisomerism here. This is something I brought up into the pencast after. You have EZ diastereomers that are potentially possible, but the stereocenter attached to the nitrogen is not impacted. So, what this mechanism looks like. We're going to start off with nitrogen attacks the carbonyl. Remember, we're doing this under acid proton catalysis. I'm going to generically reflect that proton as carried by the amine. Remember, we discussed that briefly last time. We said, in this mixture of my ketone and my amine, the best base to hold onto the proton is probably the amine. The amine will be the proton carrier for the catalytic cycle. I'm going to do my nucleophilic nitrogen attacking my carbonyl. Why? Nitrogen is more nucleophilic than oxygen, so we can do that in our first step. Second, it makes a Zwitter ion. The product of this first step here is an equilibrium to make my O minus and my nitrogen. And I'm just going to, no, I'll redraw it. I'm not going to be lazy. If I came in with 2 protons, I still got 2 protons, like that. The new bond is between the nitrogen and the carbon. What I mean by nitrogen, the nitrogen and carbon, I'm saying this bond right here is my new nitrogen-carbon bond. That nitrogen-carbon bond is not impacted, did not change. It's not impacted or not changing as part of this chemistry. It's just coming along for the ride. Now, this first intermediate needs to go through 2 proton transfer steps. And as I discussed last time, remember, we formed this Zwitter ionic intermediate because at least it's middle in terms of relative stability. The reason we're not activating the oxygen, protonating the oxygen, is because we're forming an oxonium species if we did that. That's relatively high energy compared to this as an option. Now, this is something we'll reflect different parts, as I mentioned as well. If you have been trained or looked at before where you protonate the oxygen to make the protonated carbonyl, because you know you're going to have to do that somewhere, that is fine. I will accept that on a test, no problem. I'm giving you this as an example because it's starting to lay down the logic of I am doing this addition, I'm making a zwitterionic compound. Relative to the different species that are possible, this is still your lowest energy pathway. Well, let's go through this in the next 2 steps. I'm going to go through, and what I need to eventually do, if you just look at this in terms of an inventory, the middle intermediate to get to this product over here, I need to add a proton here and remove a proton over there. That's eventually what I have to do between this, which means there are 2 proton transfer steps. Now, something also, because if you do this, this is a lot of individual steps we go through, it's a lot of drawing. There are certain times on an exam, I will tell you, you are allowed to just tell me you are doing a proton transfer. If the purpose of the question is work through the structure, tell me you're doing the structure, show me what the intermediates are, I do not have to have you draw every single arrow pushing thing to show the proton transfers. I'm asking you to reflect that you understand you need to add a proton here and take off one there, which means it would be okay to write under that warp move 2 times proton transfer, and you will get an oxygen there and minus a proton over here. Again, all I'm saying on this one is, too many. All I'm saying on this one is I'm asking you to understand that you have to remove a proton from your nitrogen, add one to the oxygen. That is official. You guys can use that. The main thing about this too is why? Can anybody give me a reason why? This is no bueno. Count off how many atoms are involved. Oxygen, carbon, nitrogen, hydrogen, that is, how big of a ring is that? 4-membered ring, that's like a cyclobutane, high ring strain, right? That oxygen minus, I don't care that oxygen minus is sitting here and the nitrogen plus is just next to it and you're like, just efficient, I just gotta do one of these, right? Remember, when you're reflecting this, what you're saying with your arrows is there is a single transition state from here to here. That is not true in this case because you're saying you're making a transition state that's a 4-membered ring that's causing this bond breaking between oxygen and hydrogen. You're forming that pickup and you're losing the nitrogen-hydrogen bond. The antibonding orbitals do not overlap in that way. They have to be 180 degrees to each other, not this weird 90-degree thing that you're trying to draw. This is total artifact. I will mark that wrong. You cannot do that in one step. And that's why it just ends up becoming a lot of individual writing. This is actually happening through 2 individual transition states where you add a proton to hydrogen from the catalyst and you're losing a proton from nitrogen back to the catalyst. It happens in step 1. I got this catalyst here. We're going to redraw that. R nitrogen, hydrogen, 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 positively charged. I'm going to go negative charge, picks up that guy to make intermediate 1, OH, NH, H plus, still chiral, and my methyl center. So I've transferred a proton from my catalyst. That's going to give me my NHHR, whatever this is. Again, this is your amine from your system. And that's going to be the species that picks up the proton in the second step to give you this guy. They're 2 discrete events handed off in 2 discrete steps with 2 discrete transition states. That's what I'm trying to reflect from this. Make sense? Yeah. I was testing to make sure you're awake. No, I'm just there. That. Good? This guy here is halfway through your mechanism. This looks like your hemiacetal or your hemiketal. Only difference is your nitrogen now, right? But this is functionally the same mechanism you go through. Normally, if this was a hemiacetal-ketal, you don't have this extra hydrogen here. If that was just, you just got an ether formation. So the only way to change this up for an oxygen-centered nucleophile, not this nitrogen, is to replace that OH with protonate it, make it water, go do something else. Because we've got this hydrogen adjacent, I have the ability, I'm set up to lose OH. If I lose water across there, that's where I can make this double bond that I'm looking for as I go through this. So the final steps of this just follows what we did for acetal formation. I now have regenerated, as part of this mechanism, this guy has made my NH, actually redraw it up here. Nah, we'll put it down there. Can I move it? I handed the proton back to my amine. I need to protonate that center. That's going to give me back my now activated oxygen species and my nitrogen. Now we're set up to lose this water. Remember, as I go through that, the other part of this equation, I've also got my NH2R. That's what happened to this guy as it donated the proton back. I've got this one. As I close that part back in, I'm going to draw it here. I'm going to redraw that down here. R, NH2. As I lose that water, I'm going to make an iminium. Double bond now to my nitrogen. Hydrogen is still present, and I still have this center. It is positively charged. So the last step here is to pick up that proton to make that nitrogen, gets me back to my final compound. So the sequence of steps here, this is where you look at the two ones, acetal formation or ketal formation, imine formation. There's a number of these steps which are common. Similar nucleophilic attacks, similar proton transfers, similar positive charge on your oxygen to eliminate that as water, resonance stabilization, all those things are common as you move through this. What is different, because your nitrogen nucleophile has a proton on it, I can now collapse back to a carbon-nitrogen double bond. I can reform my pi bond. Versus the oxygen, I have lone pairs, but anytime I borrow those lone pairs to make something that looks kind of like my imine here, I would have a positive charge on my oxygen because I have 3 bonding equivalents to it. So the very important thing as you go through this, this is the full clean sort of ChemDraw version of this. The very important equivalent as you go through this is to look at your acetal formation and your imine formation. Look at the steps that are the same, which ones are different, and why. Again, major ones here is the relative acidity, basicity of your nitrogen versus your oxygen nucleophile. Those are different. The fact that your bonding order of nitrogen is 3, bonding order of oxygen is only 2. So you're going to have different stabilities and possibilities. Nitrogen, because I have a bonding order of 3, I can collapse back to this imine form. I can regenerate my pi bond. So as a general statement, based on what we talked before, what do you think the relative stability of something like my imine, where I've got a carbon-nitrogen double bond, versus, let's say this was an acetal? It's kind of apples and oranges, but from what we've talked through before, is an imine, in your expectation, more stable than an acetal or a ketal? Yes or no? Who thinks yes? Why? I've been able to form a pi bond again, right? I had started off the carbon-oxygen pi bond. I made a carbon-nitrogen pi bond, but I still built my pi bond back in. Versus the acetal, you've sacrificed the pi bond and made this 2 sigmas, right? So in general, again, it's going to vary depending on specifics there. This is kind of an apples oranges config, but I wanted sort of bonding order. Yes, please.
Yeah, so for in your drawing, you drew like a wedge attaching to the nitrogen. But then
Okay. I may have screwed up how I drew it. That's why I like to do it here. This is the perfect version of it. I have the time necessary with ChemDraw to make sure I'm not screwing up my chirality. Apologies if I just made the enantiomer. That is correct. That is truth. That is right. Apologies for that. Again, this is what happens when I'm staring in front of it and going, oh no, actually no, let me phrase it this way. Oh, I totally did that to make sure that you guys could catch it. No, what you're commenting on is, that is S. What I drew here, is that still S? Is it? Yeah, it is, right? Oh yeah, I am totally right. Ha ha ha, take that. Okay, no. Pause. This is an important thing. Again, this is how you know you can, again, wait a minute. The carbon is a wedge, and the last one you said is nitrogen's wedge. Those are totally different things. That's this. Right? All I'm doing is the relative presentation of which bond is extracting out of the page. But remember, you can always go back. I don't care how you draw it. This is what I like to do in first year. Which hand is this, right or left hand? Which hand is this, right or left hand? This is my, it is my, it is my, it does not matter. And I only know that because the relative presentation of my thumb relative to my fingers. The R or S notation is your ground truth, not because I happen to draw the methyl up or down, right? So I apologize if that looked different than this, but that's what you always have to come down to, is this is why we do CIP, and you can actually go back to it and do it quickly. All I was trying to do is represent it where the initial drawing, and again, I will full on comp to that. There are going to be times where I will draw it wrong in the moment, but usually go through and do your CIP to make sure you're correct. But that's still that. That is still a C, S. Okay. Again, the thing I want to really emphasize here, you've been given two mechanisms that look on the surface radically different. Nitrogen doing these species, oxygen. The thing I want you to go through is look at this versus the acetal one. What is common? What is different? What intermediates are the same, and their bond motivation, the bond mobility and how those electrons move are really, really similar. They're related to each other. And the way that you can actually internalize this, make sure you know this correctly, is find those differences and understand why it looks slightly different here versus the oxygen. Yes, please. This one here, why does it keep going forward? Sorry, this one here. No, really good question. Why doesn't the reaction stop here? Give me some hypotheses. Why does the reaction choose to move forward? Because I can make a pi bond if I do it, right? That's one part. Okay, think of it in terms of reaction. If I for sure started off with these two species, and I really, really want to make this, in the laboratory, what can you do to make sure that absolutely happens? What's that? Dehydration, Le Chatelier. So first of all, on an energetic surface, I have sacrificed a pi bond, I can make a pi bond. That's the energy reason why moving forward makes sense. In terms of just doing this reaction practically, this reaction eliminates water. So how I would actually get this reaction to work is I would dry the reaction by some point. It's almost like you set us up for, ta-da! I love this. You guys are falling into every trap. So this is back to the same. This is still, even though energetically, the imine can be more stable, or at least similar stability to your carbonyls. There's going to be a problem with this a little bit. Sterics here are a little bit worse, right? Because I have no steric clash. Here now I've got carbons that are bumping into each other. So, maybe slightly higher in energy. But how I get this reaction to work productively is I use Le Chatelier again. Now, remember, acetal-ketal, we did this by saying I will pick one of my starting materials and I'm going to put a boatload of that starting material in, right? There's two things about that. One, if this was, methanol, it's a solvent, I can boil it out after, no big deal. I can use as much methanol as I want. The one productive thing we do with imines, now we're forming relatively complex structures. Does anybody know about chirality? About chirality. There's kind of a general purpose of this. If I'm making a drug and I need one chiral center, the cost goes up by about 100 times. If I have 2 chiral centers, it's about 1,000,000 times. If it's 3 chiral centers, it's about 100 million times. Chirality is special. Getting molecules with pure chiral centers, one only, is not something to take lightly. So if I had this as a Le Chatelier problem and you told me, you guys are my student, you're like, oh, yeah, I'm going to drive this to completion. Don't worry, Jason. I took that chiral amine. I just used 50 equivalents to it. I'd be like, you. That is not an effective economic way to do this. So the thing we're trying to emphasize here is, for Le Chatelier, you have two choices. Dump in more starting materials, or the far better one, get rid of products. I can pull or I can push, right? This is introducing a technique. Has anybody heard of a Dean-Stark trap? Well, now you have. Oh, yes, good. A Dean-Stark trap is just a distillation. You guys have done reflux before, right? This is a special reflux where you boil the system, vapor goes up here, and because you've offset this part here, vapor is going to travel up, it condenses up here, which means this is going to have your solvent and water. Both solvent and water will boil, they condense over to that side, and they roll, because of gravity, they roll straight down. And when they do, they end up in this side little trap where water, if this is an organic solvent, water is heavier than your organic. So water will collect at the bottom, the organic solvent collects at the top. Nice thing about that is as the organic solvent collects up, pure organic solvent rolls back. You've just set up a little conveyor belt where gas and water is going to go up, so you've got your solvent and water being condensed. They drop down. Pure water, liquid water, is going to condense here at the bottom, organic solvent at the top, where the organic solvent is being returned to your reaction flask. You've created a way, like a ratchet, to slowly distill out the water without boiling off all your solvent. Very useful technique, right? It's using an azeotrope to do this. And then what you can do, because of that tap at the bottom, is I can actually drain out the water selectively. I can actually run this for a lot of time where I'm only removing water and not the organic. This is just the practical lab chem way of doing Le Chatelier's principle. The other way to do it is a drying agent. You could use sodium sulfate or like a zeolite or something that just you add to the reaction that soaks up the water and holds on to it. That's the other component. But this is how you do it on a larger scale because I don't have to add anything else to the flask. Okay? All right, 2 problems for you to try later. Balanced chemical equation mechanism for this guy. What are you making as a product? And what would you do if you took this? How would you make it? What are your starting materials to go for this? How you're going to approach all of these is to look at the reactions, find the functional groups of interest, and either walk forward or backwards to make those ones. And again, while you may not need to do the mechanism for these, practicing it is a good thing to sort of go through. But I'll write those up after, including this one. What's the products of this one? Geometry matters as well, E or Z. Okay. Oximes and hydrazones. New names, same mechanism. If you're asked to make these products, you're using the similar constituent components. A carbonyl and a nitrogen nucleophile makes my carbon double bonded nitrogen. Carbonyl, nitrogen center, carbon double bonded, where this is coming along for the ride. There's an important reactivity that I am telegraphing with the oxime. So one of the most common questions is, what is more nucleophilic, a nitrogen or an oxygen, just at a whole? So alcohol versus amine, what do you think is more nucleophilic? So you guys think, like, again, you've heard this before, you may be repeating what you've heard. What is more nucleophilic, a nitrogen, like an amine, or an alcohol? Here you have a molecule that has both amine and alcohol. I'm telling you, when you mix this with this, that is your product. This is a reality. This is a way of head-to-head. Now again, it's not a perfect one. A molecule that has both nitrogen and oxygen right side by side does some really funky things. Has anybody heard, by the way, sides thing, has anybody heard of hydrazine before? Go YouTube video, hydrazine explosion rocket factory. Molecules like hydrazine like this, where you take 2 heteroatoms, you've got a tiger in a cage. You have 2 molecules with a lot of electron density and lone pairs barely held together by a bond. If you oxidize this, make a nitrogen-nitrogen double bond or nitrogen-nitrogen triple bond, you have just made hydrogen gas and nitrogen gas. Has anybody seen The Martian? This is how he stayed alive. because he took hydrazine as rocket fuel and he put it on a catalyst to make water by taking hydrogen generation. This is an actual reaction you can do. These are energetic steps. Yes?
If you had a product with a primary amine and a secondary amine, are you most likely going to use an enamine?
Oh, okay, so what you're saying is if I have two nitrogens, a primary amine and a secondary amine, who wins? I don't know if I could generalize it cleanly. Generally, a primary amine, less steric, probably more nucleophilic. Secondary amine, you're right, we're going to do that one. That's the enamine you make from this one. That would probably have to come down to another feature. Geography, ring size. You'd probably need some way to select between the two, so it depends on a lot of other factors. I wouldn't generalize it. But oxygen versus nitrogen, this is something you may have heard at different points, and it's living live here. A molecule like hydroxylamine, where you have a nitrogen and oxygen, the nitrogen is going to be the one that engages with the carbonyl. It's going to be a more nucleophilic center, but the second reason why is by binding through the nitrogen, I'm swapping one pi bond for a different pi bond. I'm on an isoelectric surface where I'm making something that's a similar stability. So this is a good thing. So, right into this question. The imine formations I've shown you, that's if you take a primary amine or ammonia and you react it with a carbonyl. What I mean is, if your starting material is a RNH2, two hydrogens, you will make imines. That's because you're removing two hydrogens from the nitrogen and the oxygen from the carbonyl to remove water. That's your process that you're actually going through. Enamines are different because, look, you have two R groups attaching to the nitrogen to begin with. These guys are special because this lone pair and this pi bond system means I've actually got a resonance structure which relates it back to something we've seen. This is our iminium species. So that's just taking a resonance structure, which would be moving the bonds over in this way, putting the lone pair out on the carbon. So first thing that makes them enamines different, they're formed from secondary amines, not RNH2. They're made where R2NH. That's one piece. They have to have this 1, 2, 3 centers where you're using that carbon. So it's not just impacting what used to be the carbonyl center here. The alpha center adjacent to the carbonyl is part of the game as well. The imine on its own, we're only focusing on that carbonyl. Enamines, it's now one carbon away. It's those two carbons plus your nitrogen. Why they're special is, again, we've got this resonance stability. That's a good thing. Second thing is, it puts negative charge on that alpha center. Enamines are nucleophiles. You guys may have remembered things like enolates, something like that from 203. We'll touch on those again. But they have this negative charge or nucleophilic character on their alpha center. This is why we use them, is because we can form them and they create this negative charge to allow us to do bond formation. Most of how your body makes new amino acids uses this reaction. We use a carbonyl to insert in a nitrogen temporarily, creating nucleophilic center alpha to it to stitch in other carbon bonds or to make things like fats and stuff like that. How we make carbon-carbon bonds uses this connectivity and other components. So as I mentioned, how we make these, it's going to take a carbonyl. We need our carbonyl center, like we've done before. We need our secondary amine, so it's an NH with two R groups, and we need this alpha center. This alpha center is special because it has protons. In order for this reaction to happen and end up with a neutral product, you're going to have to dump a proton somewhere. We talked about this before. If I just condense that secondary amine with my carbonyl, I've only got one hydrogen I'm losing on my nitrogen. I'm going to be left with something that has a positive charge on this center. The only way to deal with that is to deprotonate that alpha center. So enamines need these two carbon centers and a proton adjacent to it to get my overall enamine point. So these are the components you need as you go through it. How we make this, and again, I'm going to show you this from an aldehyde. You can do them from ketones. Most often, enamines are reacting with or enamines are formed from aldehyde type centers. That's productively how we typically use them. So once again, it's going to follow the same pathway we started off. Nucleophilic attack under relative acid-base conditions, weak acid conditions as our catalyst. And we're going to do an addition to make my zwitterionic intermediate. Again, only thing that's really different here, instead of having 2 hydrogens on this nitrogen, we have a hydrogen and a R group, which means we really only have 1 proton to dump just from that nitrogen center. All right, we're going to do this, and again, we're going to say that it's with a NHHRR. This is my protonated secondary amine. That's going to be my acid catalyst. Protonate my oxygen, got my hydrogen, and I'm just going to redraw my secondary amine over here. All right, when we do this, I'm going to have a free secondary amine kicking around. That's going to be my base to do the second proton transfer event. That's my neutral aminal, sort of this nitrogen-oxygen acetal type intermediate, or hemiacetal type intermediate. Now to go forward, we have to do the same thing we did before. I've got my protonated secondary amine. I'm going to use that to borrow a proton and activate this oxygen for loss. Bless you. Bless you again. All right. OH2 plus and nitrogen RR. Now again, there's 2 ways you can draw this step. We need to get rid of oxygen, the water. We have to form a carbon-nitrogen double bond. Like we've described in the other steps when we're talking about the hemiacetals. Part of what makes this possible, and again, I'm going to do it as 2 steps again here just to emphasize that one more time. If I was to just lose this, the product I make from just that one step is RH. So I'm just not forming that pi bond yet. It's going to give me a carbocation at that center where I've lost my molecule of water. Again, from there, I have a lone pair over here. I can drop that lone pair down to form a resonance structure. That's partly what's possible here to give me something that is stabilized. I've got this carbon-nitrogen double bond, my R group, and my positive charge. This is my iminium intermediate. So for secondary compound, secondary amine, all I can do is stop here, right? I have no more hydrogens on my nitrogen to deal with the fact that it's left with a positive charge. I've got carbons in there. So this is kind of stable. Iminiums can be useful for different things, but if you had water around here, it is super electrophilic. It is really easy to do an addition to that center very easily. So the only way to fix this off, that proton, is we've got 2 more protons here. That deprotonating that with some base, in this case this is my free secondary amine, can deprotonate that center and give me back to my final enamine. That alpha center deprotonation is how I get rid of this final positive charge, and that gives me my enamine structure from this point. So again, drawn out, that's the full sequence, aldehyde, and then your final formation through your cationic iminium and your final deprotonation to give your enamine structure. Okay, I will see you guys on Friday. Okay, we're going to go over the problems from today's class. So first of all, we're asked to predict the products and write the balanced reaction for the following. So we were adding together this molecule and this molecule with a weak acid catalyst in the system. If you notice, we have a nucleophilic center. We have two of these. We also have two different carbonyls. So this you should recognize as an imine formation. Just as a quick reminder, if I only had these two centers, I'd make one imine. Since I've got two of them, I'm set up to make something that looks like a diimine, or using it twice, right? And I can count that off as, let's say this is nitrogen number 1, 2, 3, and number 4. And that might add, nitrogen adds to carbon number 5 and 6. So I'm setting myself up for what looks like a 6-membered ring. Remember, when you make imines, you are using the nitrogen nucleophile to replace a carbon-oxygen double bond, and I'm eliminating water. So water comes from this H2O piece, and it's going to happen twice. So as this reaction runs, I'm going to start off by drawing the part of the molecule which is not changing. That's this diamine. We've made a new bond, double bond. So we have two of those, and we have the alkyl centers. So that's the diimine that we're making, and again, balanced chemical equation. The other parts of this is what happens to my H2O. I'm going to have 2 times water. 2 molecules of water is going to be eliminated from this reaction. So that'll be the overall balanced chemical equation is 1 new condensed compound and 2 molecules of water. Okay, now for this one. If we are trying to make this product, so this is our final product, this is our retrosynthesis arrow. So we're asked to say, how might you make this material? What are you starting from? Again, if we're just doing a like the analysis of this, you can notice there is my imine, which means I could potentially form this from some condensation reaction. I could be eliminating water, where I would have the nucleophilic amine and the carbonyl center. So that's what this is composed of. So if I'm going to draw this out, what I would do is I would identify the part of the molecule which is coming along for the ride. That would be my carbonyl center. And then I've got this pendant group over here. These pieces here make up my nitrogen. So I'm focusing on breaking down this carbon-nitrogen double bond. So that would mean I've got a 6-membered ring. The center I've indicated, this one here, would be my carbon double bonded oxygen. That's the ketone I'd be starting off with. At the adjacent center, I've got a, I'll just count this off, 1, 2, 3, and then the nitrogen is 4, so 1, 2, 3, and 4 is NH2. So this would be what I would start off with. And again, just to target out that ring, 1, 2, 3, 4, and 5, and 6 corresponds to 1, 2, 3, 4 is nitrogen, 5 is this carbon here, 6 is that carbon there. That would be the right mapping of what we're actually sort of forming through. The conditions we might use for this might be under equilibrium conditions, using some sort of an acid catalyst, and that would give us the product that we're looking for. Now for this one, we're asked to predict the products of this reaction. So once again, now we've got our nitrogen nucleophile, our carbonyl, we have acidic conditions, and we are eliminating water from this. So this is a condensation reaction as we go through. All right, so you should be able to identify my nitrogen nucleophile. The oxygen will be removed. That's where we're getting our water. So it's the 2 protons, and that oxygen is where this water is coming from, which means I'm replacing this carbon-oxygen double bond with a carbon-nitrogen double bond. So if we drew that out, we've got a C double bonded nitrogen, and then the other fragment, that's this piece over here, is attached to our 5-membered ring like this. So that would be our product. Now one of the questions you could look at though is this the only geometry of product that is possible? Is there any other isomer. And remember, when you're doing imine formation, there's a possibility that here we're starting with a ketone. This nitrogen, if I just generically, let's draw out nitrogen R prime, R double prime, there is a possibility, right, that if R prime and R double prime are not equivalent, then I could have two possible geometries of my product, right? I could have both the E and Z geometry where I have R double prime, R prime. And again, the thing I'm focusing on here is that on this one, R and R double prime are on one side of the pi bond. Here, I've got R and double prime. So one geometry, other geometry, but that's only possible if this is not symmetric. If you look over at your molecule here, I could try to redraw this, let's say where I'm drawing this in other geometry. And again, let me just do that one quickly. So hypothetically, let's say we drew this like, let me see, move it down there. I'm going to put this up here. The question then is this a different molecule than this? The answer is no, because the priority, CIP priority of these two groups on both sides is identical. There's a plane of symmetry running through here. So the two things I've now shown are the same molecule, just under a pancake flip. Okay, so for the last question, we're asked to draw the mechanism for the formation of this enamine. So this follows off the last thing that we saw in class. I'll go through it longhand again. Actually, before we do that, let me add one more page so we've got plenty of space. Okay, so step one, identify the center of reactivity. There's my electrophile, there's my nucleophile. I will do nucleophilic addition to that center, which gives me my first intermediate. So my cyclohexane ring, I'll now have my O- and my nucleophilic nitrogen coming in with proton, positive charge, and that's my zwitterionic intermediate. Remember, we're doing this reaction under weak proton. By convention, what we say is that the nitrogen is going to be our charge carrier, so we're going to have it as our positively charged component. That's the species that we're going to use for our acid-base step. And we do the proton transfer to the oxygen minus first. Again, just convention on that is we're under acidic media. If we're under acidic media, quenching the negative charges, the basic centers first, is probably what we're going to do, because yes, I'm still making a positively charged intermediate here, right? By protonating that oxygen, I'm left behind with a positively charged intermediate, but we started off with other positively charged intermediates in the mixture, so at least they're the same energy or similar energy on a thermodynamic basis. Okay, so we've done that. We now have our secondary amine. This is going to be our conjugate base that we're going to use to carry out that second proton transfer step. And after that, we are going to have our neutral, kind of hemiacetal looking intermediate. We just now have a nitrogen in that space. Like that. Okay, halfway there. Now we've got to continue this. Remember, when we do that addition, we've now donated back proton to the center, like this. We're going to now protonate. We're going to get rid of this water, so we're going to move forward by protonating that compound. So we're activating the oxygen to act as a leaving group. We now have OH2 plus, and we've got our neutral nitrogen. Okay, oops. Now, as I mentioned before, there's two ways you could look at this. Either you're going to eliminate the water, eliminate water first, which means we could just draw it in this way, which would give you a carbocation. That carbocation would be resonance stabilized by this lone pair, so there'd be a resonance isomer you could also draw. The other one I'll just go through is you can do both of those in one step. Remember, these are really equivalent to each other, showing the loss of water to make a carbocation and then resonance as compared with both pairs of lone pairs moving at the same time. These are equivalent. There's no transition state between those two. So I'm going to just, whoops, let's borrow that structure. Oh, wait, undo. Hold on. Yoink, yoink. There we go. All right. And let's go ahead and copy this. I think I can copy it. Let's go over here. Boop. Paste. Oh, anyway. Poop. I will redraw it instead of being lazy. I am sorry. My copy paste is not playing well today. Right. OH2 plus and nitrogen. Here we go. And like I drew, down and up. That's going to give me my key iminium intermediate. The iminium is our carbon-nitrogen double bond, but because it's a secondary amine, we have a positive charge in this nitrogen. We have a formal 4 bonds to this nitrogen giving us that charge, which means we're going to have to borrow one of these protons, and we actually have 2 centers, right? So one of these protons is going to have to be deprotonated in order for us to complete this mechanism. And we've got our, because we've done that proton exchange, we've got our free base, our conjugate base available to do this deprotonation. Now, which one will you choose? In this case, remember, you've got a plane of symmetry. Both of them are equivalent. It doesn't matter which one we do, we will always make the same product in this way because of symmetry. However, remember, there's a possibility that if these and these were non-equivalent, you will get 2 different enamines. That's just the regiochemistry, so left and right. As an example, let's say, hypothetically, what if I had methyl groups over here? Now, these protons are non-equivalent to these protons. They're different, which means we would get 2 different enamine products if I were to do that. But let's take this one simple, and again, I'll draw the other example in just a second. We have symmetry. It doesn't matter which one of those protons we choose. I'm going to deprotonate this one, and the way I would draw that mechanism is in this kind of elimination kind of pathway where we're sort of deprotonating the center, and we're forming a new carbon-nitrogen double bond as a result of that. So that's going to make this. We're going to have our N like that, and we've got our 1 proton left. So that's our product, and again, if I were to deprotonate these ones, I would get the same product. It's just a pancake flip. There's no special symmetry or anything else. What I was mentioning briefly, what if I had, let's say, 2 methyl groups here, double bond, nitrogen, this enamine. Now I've got 2 protons on this side and 2 different protons on this side. So in that case, depending if I went right or left, if I deprotonate at the red center, I will make this enamine. And if I deprotonate at the blue center, I get this one. These are not the same because of that break-in symmetry. We'll talk a little bit more about some of the rules for those selectivities in terms of kinetics and thermodynamics that might give you control over this, but just in general, if there's not a big difference in the relative acidity, both products would be formed in roughly like a 50-50 ratio, and probably in a case like this might be exactly what's happening. But again, we'll talk a little bit more detail of that in the next class.